So yesterday, we were talking about position versus time graphs. Okay? And we ended off looking at this graph here that was showing an object that was undergoing what? Acceleration. Are the accelerations all the same? No, they're not. Okay? We said that in part A, the object's acceleration was two things. Forward and positive. Okay? Because it was going forward and going faster. Yeah, well, that's positive. Yeah, so forward and faster. Okay. Now, if in part B here, okay, we had the object actually undergoing kind of the same acceleration, but moving in different directions. Okay. During the first part, so from here to here, the object is still moving forwards. How do I know that? Right, its position on the graph is still increasing, but its speed is decreasing. And we know that because the line is not getting steeper anymore. It's getting flatter. Okay, and we know that a horizontal line means the object is stopped. Okay, now we talked also yesterday about how we could calculate the instantaneous velocity by drawing that tangent line. Okay, and the tangent would represent the velocity of the object at that point. Okay, just to kind of reiterate that, there's a line that's tangent to the curve. Well, that's not very good. But, it's tangent to the curve at B. What's the slope of that line? Yeah, 0. Okay, right? It's horizontal, but it's tangent to the curve at B. Okay, meaning that at that very point, the velocity of the object is 0. Okay. Now, after point B here, then the object is accelerating. Actually, it's accelerating at the same rate all the way through this little bell curve part here. Okay, so it's accelerating at the same rate all the way through that, but now that acceleration is making it go backwards. It was accelerating backwards the whole time, but now it's actually moving backwards, right? And it's going to increase its speed until it gets to about here. And now what's happening to its speed? It's slowing down, which means it's actually accelerating forwards. It's moving backwards. Right? Its position is becoming more negative or less positive. Okay? But it's accelerating forwards. That's how you stop going backwards. Okay? If you don't want to go backwards anymore, you accelerate forwards. And vice versa. What do you suppose this is actually a graph, this whole motion? What is this a graph of? Nope. This is what it's a graph of. Something being thrown straight up in the air. Okay? This part of the graph right here is the part of the graph where I am propelling the marker up. Okay? So I'm exerting a force on it. I'm increasing its speed in an upward direction. The second it leaves my hand is right here. Okay? And now, what's grabbing it? Gravity. And gravity is accelerating it downwards. It's still moving upwards, so when it leaves my hand, it continues to move upwards, but it's slowing down because gravity's trying to bring it back to Earth. Okay? For an instant, at the top of its flight, it's actually stopped. And then begins to come back to Earth at exactly the same rate of acceleration as before. Okay? Gravity always accelerates everything at the same rate. Okay? And so it's accelerating downwards until it gets to here, which is the point where I catch it and slowly bring it to a stop. Okay? Does that make sense? Great. All right, so now we're going to talk about velocity versus time graphs. Okay? We're going to look at some examples of that. All right, so on a velocity versus time graph, what can I read directly off the graph? Velocity and time, exactly. So a velocity versus time graph tells me the magnitude and direction of an object's velocity at given points in time. So in other words, I can figure out how fast something is going, okay, at various points in time. Now, these two graphs, one's a position versus time graph, the one on the left. What is the one on the left showing? What's this position versus time graph showing? What's that object? Going forwards. at a constant speed. Okay, or constant velocity if we're going to give direction, let's say velocity. So this is an object moving forwards at a constant velocity. What's that graph show? It's a velocity versus time graph, guys. It's something traveling at a constant velocity. This is the same graph. Okay, well, it's not the same graph. It's the same motion being looked at from two different graphs. Okay, so we've got on this graph here, okay, it's velocity versus time, and it says the velocity is not changing. Okay, it's staying constant at 260 meters per second. Okay. This graph is showing the same thing. How can I figure that out? How do I find the velocity of the object from a position versus time graph? Displacement? Yes. Okay, I could go displacement over time. I could also find the what of this line, the slope of this line. Okay, I'm going to find the slope of this line. Okay, I'm going to say m equals y minus b over x. So I'm going to say y is 1400, b is 100, x is 5 seconds. So that's 1300 over 5, which is 260 meters per second. So graphs look very different, but they're showing exactly the same thing, right? From a position perspective, we see the position is changing equally, okay, every second because the speed or velocity is constant. On this graph, it's showing no change, okay, because the thing it's graphing isn't changing, right? But if I was to throw this graph on a unit exam as a multiple choice question, I would make the options as follows. Okay, I would say, according to this graph, what type of motion is going on? A, object not moving. B, object traveling at a constant speed. C, object accelerating. D, none of the above. You'd be surprised how many people with gut reaction pick A. Okay, because they see something that's not changing and assume nothing's happening. Doesn't mean nothing's happening. It means whatever's on the graph isn't changing. Okay, we always have to make sure we interpret that correctly. Okay, there's no change. That doesn't mean nothing's happening. It just means there's no change. This is an object that is actually moving. Okay, if it was a position versus time graph and it was a flat line, then you're right. It's happening. The object's just sitting still. Okay. But in this case, the object's moving at a constant velocity. All right. What would that be showing? That's an acceleration, okay? Because it is showing an object whose velocity is changing at a constant rate. Yep. So it's accelerating at a constant rate in a forward direction. Okay? Its velocity is increasing in a forward direction. Okay. Now looking at that, we haven't talked about acceleration yet, but acceleration can be calculated using a formula that looks like this. It's actually on your formula sheet. Acceleration equals final velocity minus initial velocity, change in velocity, divided by time. Does that look a lot like another formula we looked at yesterday? Yeah, looks like this one. Okay, which is what I did right here. Okay, everybody follow me on that? Okay, so I found the change in y and divided it by the change in x, and I got the speed, which was the slope of the line. Well, on here, the change in y is the change in velocity, and the change in x is the change in same formula, but it means something different. Okay? The slope of this graph is something else. It's acceleration, not velocity. Right? But it's not hard to figure out what the slope of a line on any graph is going to represent. All I have to do is figure out, okay, what's the change in y divided by the change in x? Okay? And I'll know what the slope represents. In this case, the slope represents the change in velocity over time, or acceleration. All right. So I can calculate acceleration off the velocity versus time graph. I can read velocity and time off of velocity versus time graph. I can calculate one other thing off of a velocity versus time graph. I want you to look at this formula here. Average velocity equals displacement over time. Okay? Do I have velocity and time on that graph? Should I be able to calculate displacement using that graph? Okay? I can simply by applying this formula. Right? Right now, this is an object traveling at a constant velocity, right? A constant velocity of 260 meters per second. And it does that for 5 seconds. How do I calculate how far it goes? Yeah. D equals V times T. Right? I just manipulate this formula. D equals V times T. So 260 times 5. Right? And that's going to give me 1,300 meters, which is exactly what I got here on my position versus time graph. Okay, everybody all right with that? What did I actually, I actually calculated displacement, but I took the height of this rectangle and multiplied it by the base of the rectangle. I really just calculated the area underneath the line on the graph. Agreed? Okay. Now, what if, this is all well and good if velocity is constant, right? That works great when the velocity is not changing. But what if we go back to having this line on there? So take it to 5 seconds. Sorry, that's too far. Whoa. That's where I wanted it. Should have just done that first time. Okay, so now I have an object whose velocity is changing. Does it still have an average velocity? Yes, it does. Since it's changing its velocity at a constant rate from 100 to 400, okay, where would I find its average? In the middle, exactly. Okay? Half the time it's going to be going faster than the middle value, and half the time it's going to be going slower than the middle value. So the middle value would be the average. Okay. Just a minute ago, we found the area of this rectangle. How do you find the area of a triangle? Base times height divided by 2. If I divide the height by 2, am I finding that middle number? Yeah. Okay. And really, all I'm doing when I calculate the area of this triangle, I'm going base times height over 2. I'm really going time times average velocity. Still using the same formula. What's that? Well, they're not groundbreaking discoveries because we've known about them for a long time. It's mind-blowing when we figure it out. Okay? All right. So that'll calculate the displacement. So anytime I have a velocity versus time graph, I can use average velocity times time to calculate the displacement. And that's going to be effectively equal to the area between the line and the x-axis. Right? And that would be true even if my graph went kind of all over the place. Okay? It might have a lot of different shapes. If I had a graph that looked like this, and actually went down into the negatives, okay, I could still calculate the overall displacement of that object. Okay? I would just have to break it up into the different motions that are present. Okay? During this part, it accelerates. So I would take average velocity times time, which would be base times height over 2. Then I'd have this rectangle where it traveled at a constant speed. So I would just go base times height, which is velocity times time. Okay? Do the same thing for this triangle. The same thing for this triangle. For this rectangle, for that triangle. And then I would do what with them? Add them all up. Okay? These ones, though, down here, would all be negative. And that gives me my overall displacement. We're not really doing anything different than we would have done with a word problem. We're simply using V equals D over T. All right. So we have a velocity versus time graph of a runner. What's going on in the first 5 seconds? They're accelerating, okay? But it's a curve, okay? At least for this little bit here, which means the acceleration, here, okay, during like this part right here, the acceleration is pretty uniform, okay? But here it's not. Okay? The acceleration is not uniform. It's still accelerating because its speed is changing according to the graph, but it's not uniform. When you first come out of starting blocks, your acceleration isn't very uniform because there's a fair amount of like slippage, and your first few steps are very irregular. Okay? Really good sprinters are not going to be as irregular, but and then you'll get into a point where you accelerate pretty uniformly once you're kind of upright. You're accelerating uniformly for a while, and then even though you're running as hard as you can, you simply can't run any faster, and that's when you reach your top speed, okay? And you run at that top speed for the rest of the race, if it's a sprint, okay? Something else, you got to pace yourself, okay? And then what happened here? They crossed the finish line and came to a stop. Okay? Does that sort of make sense? Okay. This person probably didn't run very far, given that they only ran at 8 meters per second. I say only. Okay. 8 meters per second isn't all that fast. Okay. To give you an idea, Usain Bolt's top speed is like 16 point something. He's a freak. Okay? It's crazy what this guy would do. Okay? Did you guys ever watch Usain Bolt run in his prime? Okay? Like he was always like the last guy out of the blocks, but he would just reel everybody in and be way past them by the end of the race. That'd be really frustrating to run against him. Because you're like, yeah, I'm winning, crap. Okay, because the guy was just so long that he could just reel everybody in. He didn't need a great start because he could accelerate for a much longer period of time than everybody else, get a much higher top speed. It just took him longer to get there. Okay? But once he got there, he got it. Okay? That's why actually the 200 was an even better race, because he could accelerate for so long. Okay. Velocity versus time graph. What's this object doing? Okay, it's traveling at a constant velocity of what? 5 meters per second. Okay, what's the acceleration of this object? 0. How can you tell that? Okay, the line's flat, so obviously there's no acceleration. It's not accelerating, so there can't be a number. But what does the equation also say? That the slope of the line is 0. Okay. Calculate the total displacement of this object. Well, the displacement's not 0, but we should be that fast. 50 meters forward, positive 50 meters. Okay? How do we do that? Well, remember, the total displacement is the average velocity times time. Our average velocity is 5 meters per second because we're not accelerating, and we do that for 10 seconds for a total of 50 meters. Now, this gets a little bit trickier when we start getting graphs that are straight lines and that have y-intercepts that aren't 0. Okay, so it becomes a little bit trickier then. So looking at this graph here, okay, we have a y-intercept that's not 0. So I would do a question. I would do something like this on a test for a velocity versus time graph. For 1 mark, I would ask you, what's the acceleration of the object? It's the slope. That's why it would only be at a 1 mark. Keep that in mind. Okay? In any course like chemistry or physics, if it's a 1 mark question, it probably involves no work whatsoever. The answer is likely right in front of you. Okay? We just finished saying that this formula that calculates acceleration is really this formula. Okay? Because on the y-axis is velocity, and on the x-axis is time. So this is the change in velocity, final minus initial, divided by the time. Okay? It's not something we memorize, we just look at it, think critically about it. All right, now for this one, I want you to calculate the total displacement of the object. one's tricky. Actually, you know what? I'm going to have you do this one second. I'm going to quickly build a different one. Okay, let's try this one first. All right, I'm going to walk through this one with you. Okay, so on this particular graph, if I want to calculate, okay, the total displacement, okay, I want to take average velocity and multiply it by time. The problem here is that according to my graph, I wasn't stationary at the beginning. Was I? Okay, so that means there's how many different shapes here? There's two. There's a triangle and a rectangle. Yeah, there's a triangle and a rectangle. Okay, and here they are. Okay. Because my line starts at 4.14 meters per second, I actually have a rectangle underneath. That rectangle represents how far the object would go if it stayed traveling at 4.14 meters per second. Okay? Obviously, it's going to accelerate, but I've got to add on to that how far it will travel while it's changing its velocity. But because it was moving at the beginning, I have to take that into account as well. Okay? If I just calculate the area of the triangle, I'll actually get the wrong answer because it'll be assuming that I started from zero, and I didn't. I didn't start from rest, okay, in this particular question. So I've got this rectangle and this triangle. So I have to recognize the shapes, and then I have to recognize that I still want to do this. D equals average velocity times time, and D equals average velocity times time. Okay, but I'm going to calculate it differently because in one, the velocity is constant, and in the other, it's changing. Okay, so for the rectangle is easy. The rectangle has a height of 4.14, okay, and a base of 10. Okay, so we're looking at 41.4 meters, okay, for the rectangle. Are they all right with that? Okay. What's the height of the triangle? Well, the answer is we actually don't know. We're going to have to calculate it. Okay? I know that the triangle, the bottom of the triangle starts at what number? 4.14. But I don't know what this is. I can't use, and this is the temptation that people do, is they go, oh, I'll just use this point. Is that point on the line? Then I can't use it. I'm trying to find stuff according to the line, not according to my points. Okay? So I know the time. I know what x is. Can I calculate y? I can because I have the equation. Right? So I can calculate what y is here at the very end of my graph. I just plug in 10 for x. Okay, so I'm going to calculate what y is. Y is going to be 3.3 times 10 plus 4.14. Okay, so 3.3 times 10 plus 4.14. Okay, so I'm getting 37.14. Now, I want the height of the triangle, so actually what do I have to subtract? 4.14. Yeah. Okay, because it starts at 4.14. So I'm going to get 33, right? So the height of the triangle is 33. That means that this object changes its velocity by 33 meters per second between time 0 and 10 seconds. All right, so I've got that now. Now I can do this calculation. My average velocity is going to be the base times the height divided by 2. So 33 over 2 times 10. Okay, 33 over 2 should be 16.5. Okay, so 16.5 times 10 is 165 meters. Okay, so we have that plus this will give us our average velocity, our total displacement. Okay, it's our total displacement because we multiplied velocity times time. Okay, all right. Now, for this one, it's going to work a little bit differently because my y-intercept is negative. All right, and that's okay. All right, we can still deal with that. What we want to do then, okay, is figure out what's x when y is, because we need that, otherwise we won't know what x is, what the time is. Okay, everybody kind of follow me on that? We want the base. The base actually doesn't run from a time of 0. The base runs along here. So I can find x, okay, by saying that that's y minus b over m, and that's going to be 0 minus negative 0.182, okay, divided by 2.96. So actually what I'm calculating here is what we call the X-intercept. Okay, we've been dealing with the Y-intercept. So we're going to have 0.182 divided by 2.96, so it's going to be a small number, right? All right, so this whole triangle starts at 0.6148 seconds and goes to 10. Right, so if I go 10 minus that, will I have my total time? All right, so there's my total time. Okay, now I want to calculate the height of my triangle. How do I do that? Same way I did on the last graph. I solve for what y is when x is 10. Okay. Okay, so that'll get me y, which will be the height of my triangle. Okay, 2.96. Okay, well, we'll just say 29.6 because we'll be smart about it. Okay, plus or minus 0.182. All right, so now I've got the height of my triangle, and I know the base of my triangle is this number here, so I'm going to take this number, divide it by 2. Okay, and then multiply it by 9.9385135. Why am I 14? Why am I keeping all the decimals? I have to. Significant digits, right? All right. So the total displacement of that object is 146 meters. That would have how many significant digits? 3. Okay. I know these numbers down here actually only have 1, but I'm going with the numbers I used up here. All right. Everybody okay with that? Then, here's what I'd like you to try. Doesn't change anything. Doesn't change anything. Okay? I want you to calculate the total displacement of this object. Actually, let's do this first. What's its acceleration? Okay, it is negative, but what number? 3.2. Okay, slope of the line is the acceleration here. Change the velocity. All right, calculate the total displacement. Okay, when we wanted to calculate the displacement before, we took average velocity multiplied it by time. Agreed? Okay, so I know that my initial velocity is 27.5 meters per second. I know my final velocity is 0, according to my graph. Okay, that's where the graph, or the line at least, ends on this graph. What I don't know is my total. Okay, I don't know that, but I need something else to get it. Time. Okay, I don't know where this line ends. It's close to 9 seconds, but close only counts in horseshoes and hand grenades and nuclear weapons. Okay, so we need to have a more exact number. Okay, so I need to solve for x when y is 0. Okay, what's y at this point right here? 0. Okay, so I need to solve for y when x is 0. So y will equal, okay, negative 3.02 Actually, sorry, I've got to solve for x. Sorry. Solve for x when y is 0. So x is going to be y minus b, so that'll be 0 minus 27.5 divided by negative 3.02. Everybody all right with that? All right, so I'm solving for essentially my total time. Negative 27.5 divided by negative 3.02. Right, tells me that the time is 9.105 seconds. Now I'll use all the decimal places when I do my final calculation. All right, so if I want to find now the total displacement, that's going to be my average velocity times time, and my average velocity is going to be my where on here? It's changing from here to here uniformly. What's that? In the middle. Right. Okay, it's going to be halfway. Remember, we're calculating the area here. That's going to be the base. There's the base, 9.105, times the height over 2. That's time times average velocity. That's all I'm doing here. Okay, so I'm going to take that 9.105 with all the decimals, okay, times 27.5 over okay. So I've got a displacement of 125 meters. Now, is it okay that that number came out positive? Yes. Which direction was this thing going? Forwards. Was there any point where the velocity was negative on this graph? No. The acceleration was negative the entire time because the object was slowing down, right? Okay? But it was always moving forwards. That's another multiple choice type question that I would snag people on, right? If I asked you a question like this and said, what direction is the object traveling? A lot of people would say backwards. Just because the line's going down and because the acceleration is negative. But in actual fact, there is never a point on this graph where the velocity is a negative number. This object was always moving forwards. Okay? It was accelerating backwards, thus slowing down, but it never moved backwards. It came to a stop at time 9.105 seconds. Okay? So that's interpreting graphs. Those are the kind of things that we're going to be asked to do, okay, on these types of things. All right, so just notes here about velocity versus time graphs. Obviously, on a velocity versus time graph, the vertical value of any point is the instantaneous velocity at that time. In other words, how fast the object is going at that time. Okay, and then it's talking about that runner's graph. Okay, the area under the line on a velocity versus time graph is equal to the displacement of the object from its original position. Okay, and that can be calculated using the area under the line is the displacement because what we're really doing is multiplying the average velocity times time when we do that. Okay, so you have a couple of graph examples there, okay, but I'll just kind of redraw it here. Okay, the other thing we need to remember, and it's not on here, okay, is that acceleration equals the slope, okay, and the mathematical reasoning for that is acceleration equals VF minus VI over t, which is y minus b over x. Questions on that? Okay, then we're going to work through some like sample problems here, okay, with graphs, and I've got a bunch of graphs in the workbook here, okay, which you're going to answer some questions, do some calculations on, okay, that kind of thing. So I'll put those up right now. Okay, starting at the bottom of page 3 in the workbook package that's on Google Classroom, that's the file I have open right now, the Unit 3 Physics Worksheet package, okay, are some graphs. I want you to perform the calculations asked or requested in the question. The answers are in bold, so you'll know if you did them right or not, okay, and you can check them. If there's any that give us trouble, then we'll walk through them together. There's probably a couple that I'll walk through anyway. Right? But let's say for now, let's get started on those. Okay, you'll probably want to have this open on your phone so you can like make it bigger and actually read it better than doing it on here. Plus, I can only really have about one question on the board at a time this way. Okay? So you'll probably want to have that open on your phone. All right. First off, anytime I have a graph, first thing I need to do is look at it and figure out what kind of graph it is. Because if I don't identify it as the right type of graph, I'll do the wrong calculations on it. Because obviously I calculate things differently on a position versus time graph than I do on a velocity versus time graph. Okay? On a position versus time graph, if I want to calculate displacement, I take the positions and I subtract them, and I'm done. That's a lot different than calculating triangles and rectangles and average velocity times time, like I would on a velocity versus time graph. So the first step is, what kind of graph is this? This is a position versus time graph. All right, so total displacement in this graph. Well, we calculate total displacement by going final position minus initial position. The final position, according to this graph, is 0.5 meters. The initial position is 0.2. So 0.5 minus 0.2, positive 0.3 meters. Okay, that's all there is to it. Final position minus initial position. Okay, we okay with that? Well, I want to calculate the total distance. Does that care about direction? No. But I need to look at this graph now piece by piece, not as one complete whole. Right? How far do I go here? 0. Just go anywhere. The position doesn't change during that time. Okay? During this part of the graph, it goes from 0.2 to 1, which is how far? 0.8. Here it goes 0. Okay? And then from here it goes from 1 to 0.5, which is 0.5 meters. So my total distance traveled is 0.8 plus 0.5, 1.3 meters. All right, average velocity and average speed. Well, I just calculated the two things I need to get average velocity and average speed. Okay, average velocity is total displacement, which I just calculated, divided by time, which I can read off the graph. Okay, so my total displacement was positive 0.3 meters divided by, how long does this graph take? 7 seconds. Okay, when I do that, I should get 0.04 meters per second, and it's positive. Okay, and then to calculate average speed, total distance over total time. Okay, that's 1.3 divided by 7, which should give us 0.19 meters per second. Okay. You good with that? I think probably a lot of people were still stuck in velocity versus time graph mode when we first started that question. Okay. Okay, so you still have here for 2 and 3 position versus time graphs. Okay, so they're both position versus time graphs. And it has to do with, if anyone has gotten already to question number 4, where it asks about the acceleration. Okay, the units I have here are meters per second squared. And those are the right units. Okay, I'm going to explain to you why the units for acceleration are meters per second squared. Okay, when we do a calculation using this formula, okay, we're dividing change in velocity, which has units of meters per second, by seconds. Okay, now let me show you what that looks like as a fraction. Okay, That's meters over seconds divided by seconds over 1. When you divide fractions, what do? You flip the second one and then multiply. Okay, so that means I've got meters over seconds times 1 over seconds. What's meters times 1? Meters. What's seconds times seconds? Seconds squared. Okay, what we're really finding here is meters per second per second. That's the rate at which we change velocity. How many meters per second am I going faster now than the last second? How many meters per second am I changing my velocity by? Okay, we just write it, say it as meters per second squared because it's faster than meters per second per second. Okay, it doesn't sound like we're stuttering or something like that. Okay, it just sounds like it's quicker. Okay, so we always write it as meters per second squared because mathematically that's what it comes out to. It doesn't mean the number is squared. Okay, so don't make that mistake. It does not mean the number is squared. It just means that there's 2 sets of seconds in the units. Okay? All right, any other ones giving us trouble so far? Any ones we need to go over? Okay, how many people are onto the velocity time graphs? On this graph, I drew in all the shapes, okay? Because during the first 2 seconds, the object's stationary, right? Its velocity is actually 0, and so there's no area to calculate. The average velocity is 0, okay? Then it accelerates from 0 to -3, then accelerates from -3 to +2, and then travels at +2 for a few seconds, accelerates from +2 to -6, and then from -6 to -2, travels at -2 for a while, and then accelerates back to 0. Okay, so I've got to find all those displacements, taking into account that the velocity changes for parts of it. So for this little triangle right here, we'll say triangle number 1, right? We are looking at an average velocity that'll be, the height over 2. So we're going to take the height, which is -3, and the base, which is also 3 seconds. Okay, that's going to give us 3 times 3 is 9, divided by 2 is 4.5. Okay, so that first triangle there, okay, is 4.5, -4.5 meters. Then I've got this little triangle here that has a height of 3 and a base of 1. Okay, so 3 times 1 is 3, divided by 2 is 1.5, and it's negative. Okay, so I'm just going to write a 2 in there. Okay, this will be 3, 4, 5, 6, 7, 8, and 9. So there's 9 different shapes I've got to calculate the areas of. Okay, so shape number 3 is this tiny little triangle. Okay, it's 1 second by 2 meters per second high, so it's going to have an area of 1 meter, positive 1 meter. Okay, then I've got 1, 2, 3, 4, 5 seconds on the base times 4, right? So that'll be 20 meters. Okay, then I've got triangle here number 5. It's only a half a second on the base. So 2 times 1/2 is 1, divided by 2 is 0.5. Okay, then I've got this long skinny triangle that's 1.5 seconds by 6. 6 times 1.5 is 9, divided by 2 is -4.5. Okay, then I've got this triangle here that goes from 2 to 6, so it has a height of 4 and a base of 2. So 4 times 2 is 8, divided by 2 is 4. Okay, then I've got this rectangle that's 1, 2, 3, 4 along the base, okay, and 2 high, so 2 times 4 is 8. So actually 8 equals 8. That's cool. Okay, meters. And then triangle number 9 here is -2 high by 1, so it's -1. All right, what do we do with all those numbers? Add them all up, okay? Keeping the negatives, and that's how I arrive at -12 meters. When I add them all up, I should get -12 meters for my displacement. Is that a lot of little tiny calculations?
Yes.
Yes, none of them really hard. There's a lot of them. Obviously, on a quiz or a test where time is a factor, I probably wouldn't give you a graph with 9 separate things for you to calculate. Probably be like 2, okay? But still, it's the same idea. All right, tomorrow you're going to have a quiz. That quiz will be on position versus time, and velocity versus time graphs.
Yay!
Okay, I will post it later on today.